Hope you all had a good long weekend and ready for new material. Today I'm going to talk about privilege separation. And it's a little bit of a more higher level lecture than, for example, last week where we were in the weeds, of buffer overruns and exactly how to bound memory references. Today, this is a much more higher level lecture and sort of more perspective of an approach to design secure computer systems. In particular, this is an approach to design systems to have security in the presence of bugs. So it's a way of thinking that even if the attacker could tickle some bug through some network packet that would cause maybe could lead to an exploit, we want to set it up that despite those kinds of bugs, it doesn't really throw the whole security plan out of the wind. So that's the goal. This is also relates to Lab 2. You're going to be using privilege separation in Lab 2. And so it's important in that respect. This is one of those ideas. It's a very important security idea. You'll see it everywhere. It's widely used. And in fact, we already have seen it. We saw it in the Google architecture paper where they talked about how they separate different servers and run on different machines and have those different machines have different privileges so that if one gets compromised, the whole security of the whole system is out of the window. But it's actually very hard to find good readings or good case studies that describe actually how you do it in practice. It's a little bit like sort of modularity in software engineering. If your software should have modularity, that's a good idea. Actually, how to do it is a little bit more difficult and challenging to sort of state and give guidelines for. And privilege separation has sort of the security equivalent of modularity. If you have a good design, a good privilege separated design, you're likely to get good security, or at least one attack doesn't really destroy the complete security of your system. And so the paper for today is one of the few papers that I know that actually gives sort of a detailed discussion about how they did the separation and what the issues were. If you read around or Google around on the web, you see lots of blog posts about people doing privilege separation, but they're pretty high level, so they don't give a lot more specific details. This paper does. And so it's a good case study to sort of really think about how you can apply privilege separation. And Lab 2 basically is based on this paper. Zookeeper is basically a sort of a similar thing as OKWS. Okay. So that's the plan for today. And so when designing a computer secure system, and a number of people ask this, plan 1, of course, is to avoid bugs. Or plan A, avoid bugs. And that's, of course, a great idea. If you can make that work out, then that is likely to improve or realize strong security. However, it's difficult to actually really do bulletproof, right? And we've already seen this. If we think back about the last lectures on buffer overrun, in the last lecture we talked about all kinds of mechanisms that reduce the way that you can exploit buffer overruns, but none of them all were actually perfect. They just raised the bar, but not made it impossible. So it's actually hard. So you think about this, we've been at this for a couple decades now to squash buffer overruns, and we're still not done, right? It's still possible. And so this plan of having no bugs or avoid all bugs is a hard one to execute on. And think a little bit about, to make this a little bit more clear, let's talk a little bit about bugs in web services to get a little bit more sense, how hard it is to actually just basically squash all bugs. And so clearly there are buffer overruns, as the paper also discusses. But that's not the only class of bugs that typically show up in web applications. Correct? And most of you are probably familiar with many of them. But there could be bugs in SQL escaping, correct? Where if you're not very careful, the website takes user input that comes in through an HTTP request and sticks it directly into an SQL query, and that can actually lead to large problems because the attacker can decide what goes into the SQL query if you don't appropriately escape the input from the network. So that's a common problem that shows up. There are many other type of problems like forgetting to put access controls in, access checks. Some developer writes an application, for user A should have permission to do it, user B shouldn't be able to do it. In one corner of the website, somebody just forgets to put that check in, and an attacker might be able to exploit that. The paper mentions a number of attacks or like problems with not handling dot incorrectly, or particularly like path names. So for example, developer opens some file, the file name is actually supplied by the attacker or the user. The attacker picks a clever path name, etc. / passport, and basically gets access to files in the system that it shouldn't have access to, but because the application didn't check that it actually was referencing files that the attacker shouldn't have able to access. And in fact, if you Google around on the web, there's going to be, you find many more. And so these are just whole classes of bugs that are pretty common. People know, they happen, and there are checkers and there are fuzzers and all kinds of stuff, to see if websites actually have these kinds of problems, but they still happen no matter what. And so this suggests, and so one way of thinking of this is that, maybe bugs are just unavoidable. There's going to be somewhere some bug, and if the attacker gets access or can trigger that bug and turn it into an exploit, then you might have lost. And so another plan, and this is sort of plan B, is try to tolerate bugs. And in practice, what people clearly do is do plan A and plan B. And you can think about plan B as sort of a defense in depth. You first try to execute as well as possible on plan A, and you do your utmost best to have no bugs. And just in case that you miss some, you also do plan B for the case that you miss some bug. And so, and basically plan B is privilege separation. And there's a very high level, what this is let's say you have a piece of software, a box with software in it, it has some secrets, S1, S2. And this is the non-privileged separated design. Let's say there's a bug somewhere in here, right? There's a bug here. Some trickers, the attacker is able to tickle this bug, turn it into an exploit, and it can steal both S1 and S2, right? Once you have one bug in this particular piece of software. So the idea of privilege separation is to design your system differently. And take your system and chop it up into pieces that are run isolated from each other. So you say maybe multiple boxes, each running with some code. And for example, S1 is in one box, and S2 is in the other box. And maybe every box has its own storage. And the idea is that now, if maybe one box gets compromised, then hopefully that action doesn't immediately lead to a compromise of the second box. So maybe the attacker can steal S1, but the attacker might not be able to steal S2. And that's sort of the basic idea of privilege separation. You're going to try to run each of these boxes with sometimes what's called minimal privilege or least privileged, so that if one box gets compromised, the attacker only gets the privileges for that particular box and no other privileges. Now, of course, sometimes you need some form of sharing, so there may be some communication between S1 and S2, but that's sort of the basic idea. Like another way of saying this is like, just don't put all your eggs in one basket. Spread them around in multiple baskets so that if one basket falls, you still have the other eggs. All right? Good, so what is the benefits of this approach? So there are two main benefits. One is it limits the damage of an attack. Because if the attacker compromises one part of the system, hopefully he's not able to compromise other parts of the system. And this really comes down to this least privilege. That every box runs with the least amount of privileges, so that a compromise of one part doesn't give the privileges to actually access other parts of the system. So that's one major benefit. The second, typically major benefits of this, it limits access to buggy code. Presumably, each of these boxes, like there's a large amount of code on this side. Let's say 100,000 lines. After privilege separation, maybe that 100,000 lines actually divides up into 50,000 lines programs, and there's just less code in each box. So there's also less opportunity to exploit bugs because less code, less bugs, right? Sort of to first order of degree. It's a little bit simplistic, to state it in that way, but that's sort of the general idea. If there's less code in one of these boxes, or more specialized to one purpose, then the attack surface, the attacker is available, is smaller. And so often this is also phrased in terms of it reduces attack surface. Does it all make sense? Okay, so this sounds all good, right? Seems like a brilliant idea. We're going to have an approach. We just separate things into pieces, and it's like modularity. We take a big program, split it into little pieces, and as a side effect, we might be able to get a better security because if there's a compromise, it will only be a partial compromise. And it turns out, that actually executing this plan in practice is not that straightforward. There are a number of challenges. So let me talk a little bit about the challenges. So the first challenge is, what is the separation plan? I drew here basically this box, split it in two, and then I was done. But I didn't really articulate any particular way of choosing how to actually split the box. And you can imagine lots of different ways of doing it. And we'll talk about it in a second when we look actually at OKDOS in detail. But the OKDOS paper already had a little bit of that in the design discussion, correct? There was a discussion about should the system be split by user, or should the system be split by surface? And that's an important decision. And so you have to figure out, what actually this separation plan is that actually makes sense for your particular application. And again, it's sort of similar to modularity. Your software should have modularity, but actually figuring out exactly what the right APIs are and how to split your software in different pieces is typically not a straightforward thing to do. And so this is also true with privilege separation. How to isolate the different pieces will turn out to be a difficult problem. So for example, the paper uses Unix processes and change root, set UID, and a whole bunch of Unix mechanisms to sort of cleverly set things up so that the individual processes are reasonably well isolated. And it turns out, experts can do that, but it actually is, quite difficult to get right. And so, for example, today, probably we wouldn't do it the way the paper does it, but one would use containers. Like more modern mechanisms to actually, get process isolation. And in fact, in Lab 2, you'll be using, Linux containers to actually do the privilege separation and put the isolation in place. And so we'll talk a little bit about isolation in more detail. Then how to share. It's typically the case in many applications that you can split things up nicely into pieces, but when the different pieces need to share, you have a problem. You've got to figure out actually how to make that happen. And this partially comes down to, like, this is related to this question: how do you, what's the separation plan? Right? So, for example, if you implement an email service, separating by user is probably pretty easy, right? Because when you're reading or writing email, you only need to have access to your inbox or your mailboxes, and not to any of the other users. So in that case, there's little sharing, and the separation plan might be straightforward. In the case of OKWS, it's just going to be more complicated, right? Because there's going to be a matching service that needs to look at the profiles from different users, and so you can't just split things up by user, because then you have many boxes that are per user specific, but then if you want to do a matching, you have to sort of figure out a way to collect all that information from the different users. So there's typically some tension between what the application actually must provide in terms of sharing and actually how you want to do the separation and how to do the sharing. And then the final thing, and this is certainly a major theme in the paper, is how to maintain performance. So those are the four, sort of generally the four top-level challenges, we're sort of implementing or applying this, design approach of privilege separation. And to make this basically, so many of these questions, have an application-specific constraint in them, right? Like I said before, like for an email service, this might be simple, but like if you implement the matching service for OKWS, that might be more complicated. And how do you go about doing it then? And so there are no general rules for how to do this. And so the best thing we could do is look at some case studies and learn from the case studies. And then you can apply it in Lab 2, and you will get more familiar with the idea about how you could apply privilege separation. And so the particular case study for today is this system called OKWS, a web server system that takes basically privilege separation very, take it to the heart and really try to do a good job at it. This is the background on OKWS. A number of people asked about this. OkCupid was founded by the same people that did OKWS. And in fact, the way it went is, they founded OkCupid. Max was very concerned about the security, because a dating website, presuming a lot of personal information on the dating website. So he wanted to have a strong plan, for security, so that he had some confidence that, the data of the users wouldn't get stolen. And so that's why he designed OKWS. And, as far as I know, OkCupid is the only site in the world that uses OKWS. I don't think there's any other one. But this idea of privilege separation is absolutely widespread. And this is just one of the few papers I know that actually has a detailed discussion about privilege separation. Okay, does that make sense? Any questions about OKWS and OkCupid in terms of background? Yeah?
Why do you think there hasn't been more uptake of OKWS as a model?
Oh, there's many reasons for. I think one reason is that it's C++. And I think web development programming languages has not gone the C++ route. It's going to go the different route, right? And that's one reason. Yeah.
Why was it ported to another language?
I presume OkCupid currently, I'm sure uses other languages too. There's a lot of websites didn't take privilege separation very seriously, right? And only later on they tried to take it seriously, and then it's hard to retrofit. And in some ways, you have to decide right up front that you're going to do privilege separation, and then OKWS is a great framework for you. But if you don't decide to do that right up front, then maybe it doesn't buy you that much. Yeah.
Modern, other websites used for privilege
They do containers. So like you think, are people familiar with Docker containers? Okay, good. So like, a lot of people, use containers, to do privilege separation. If they do privilege separation. There's also a lot of sites that just don't do privilege separation. Any more questions? We're gonna, tomorrow, the TAs will run a recitation section in lecture today, in the same place as here, where we're gonna talk a lot about the details of containers and all the machinery that you will be using in Lab 2 to do privilege separation. All right? I'll touch up on it today a little bit, but we're gonna go in much more detail tomorrow to make sure that you can actually do Lab 2. Any questions? Okay. Okay, so let's so dive in and see, look into this case study and sort of see what we can learn, from privilege separation through the lens of this OKWS design. So the first thing they do, is maybe the right starting place, is they divide. This is basically figure 1 of the paper. They divide, the website into different services. Service 1. Whatever. And that's their primary privilege separation plan. They're going to take the service offered by OkCupid, split it up in different pieces, and where every service is actually individually isolated. So what are some examples of these services? You read the paper. What do we think about these boxes? What's in these boxes?
What is like the database proxy?
Yeah, okay, let me draw it a little bit lower. I think the database proxy is almost like a side effect of having these services. So what are some example services? So there are services that are basically like infrastructure to actually support these services, and then there are actually services that are the core functionality of the website. So what is in the website?
There are endpoints on the website.
Yeah, there are endpoints on the website. So what kind of functionalities on it? Has everybody used OkCupid? All right, what's there? Well, we can guess, correct? They talk a little bit about it in the paper. It's sort of important to understand, right? What's there? Yeah.
Login services.
There's logging, absolutely. There's probably an authentication service, right? So there's presumably a logging service. Anything else? Yeah. Yeah. They talk about a matching service, right? Any others? Yeah. Messaging. Yeah, messaging. Any others? Yeah.
Uploading photos.
Yeah, photos. So that's a photo service. Any others? Any other people can remember or recall? There are a few others that they at least mentioned in the paper. I imagine there are many more, but like the profile editor. And who writes these services? Yeah, the developer that uses the OKWS infrastructure, correct? And so, what is their assumption? Are these very experienced developers, or are these developers that are more in tune with like web programming as opposed to infrastructure programming? What is the inexperienced programmers, right? These are, they want to set it up. Their assumption is that these are basically the sort of the rich functionality of the website, probably written not by the infrastructure people, but they're actually people that do the sort of the end user visible services programming. And the main concern, basically, that I think Max had when designing the system is that he wanted to make the assumption that the inexperienced programmers are going to make bugs when writing these services. Whether it is the form of missing access control checks or any other form, he was imagining that this was going to be a tricky thing to get 100% bug-free because it's going to be written by inexperienced programmers. And so we wanted a system that even if one of these boxes had bugs, it wouldn't violate or it wouldn't really compromise all the other services on the system. Right? And so this is the unit. If you think about this, this is the separation plan that OKWS has, it's separated by service. Okay? Now, to support this infrastructure and to make sure that we actually do get strong isolation, there's a number of things that sort of sit around it to help set up this infrastructure. One of them is the database proxy. And the database proxy talks actually to the database. And so why that? Why not have the service directly talk to the database? Why have a proxy in the middle? Would be more efficient, right? One of our goals is to actually maintain performance. So let's get rid of the proxy. Yeah.
Because you don't want the credentials of the actual database to be stored on the untrusted services?
Yeah. Any other?
The escaping bugs, those are, because you could still have some other service to the authentication, but
Yeah.
you could still have some bug that could be used to exploit the SQL escaping thing.
Yeah, so I think you guys both identified two important reasons. I think one reason is SQL injection attacks. So he was very worried that inexperienced programmers would take input that is coming from the network, some user ID, plug it into an SQL query, send it off to the database, didn't do the escaping appropriately, and instead of doing a lookup in the database, it turned into like a delete of all the records in the database. So number one concern is SQL injection, and so he doesn't want these inexperienced programs to write any SQL instruction at all. So the only way for a service to get to the database is through some RPC, remote procedure call, to a specific set of functions or APIs that's defined by the database proxy. And so think about this as like REST APIs, if you will, in terms of like modern terminology. Right? Yeah.
My ask that deeper is, are the DB proxies the same thing as a regular service, like implementation-wise, or is it something different?
I think it's first order, like any other service, like any other box in that picture in figure 1. It's some Unix process that has an RPC interface. And in this particular case, it's an RPC interface that allows you to access parts of the database. And that talks with another communication channel to the actual database and issues the SQL queries. So all the SQL queries are actually issued inside of the database proxy. That's the only thing that actually issues SQL queries. And the database proxy, is that written by an inexperienced programmer or an experienced programmer? Very experienced programmer. Right? That's the intent here. That is like Max writes the database proxy and hopefully doesn't make any, doesn't forget to escape any SQL inappropriately. Okay, does that make sense? So then the second part, as somebody also mentioned, is that the database proxy both basically does the constructs the SQL queries, but it also does access control. So when different services may be talking to the database proxy, issue RPCs to it, and the database proxy performs access control based on the identity of the service. So for example, let's say the matching service. Should it have access to the table with passwords? No reason for it to have access to the password table, correct? And similarly, presumably for the messaging system, really doesn't need to have access to the profiles of the different users, correct? And so they want to enforce, so this sort of access control where services don't get access to the full database, they only get access to the piece of the database that they need. Right? And the way that works out in this system is that with every service, there's a token associated. And in the RPC, you have to supply the token, and the token is used to do access control and decide which part of the database are actually allowable. Right? That make sense? Okay, so there's a bunch of other support necessary to actually set this all up. Okay? It has to come into existence. And in fact, there's another piece to it. somewhere the HTTP requests have to come in, right? So on top of this, there's something that's called OKD. And OKD, that's a place where all the web requests are going to come in. So here's all the HTTP traffic comes in, and OKD looks at the first line, basically, of the HTTP line, very much like what you've been looking at in the code in Lab 1. You think about Lab 1 code as OKD. That is a pretty good mental model. And so OKD looks at the first line of the request, and then decides to which piece, to which service to route it to. And again, using the internal RPC system that they have. That make sense? Now, OKD listens on port 80, which is the sort of the default port for HTTP traffic. And port 80 actually on most Unix systems is a privileged port, meaning that the process that wants to listen or read and write from port 80 needs to have privileges. And so, but they don't want to set up the system so that OKD actually has privileges, like super user privileges. I mean, why would that be bad? So there's a little bit of a conundrum here now, correct? We have OKD that needs to listen on a port 80, but to be, listen to port 80, you need to have root privileges, which basically makes you super user, and you can have complete control of the system. So why would it be bad if OKD actually really had root privileges?
Because it's exposed to all the web traffic, so it's the most external facing part of the system.
Yeah, this is the most external facing piece of this website, correct? I mean, this is the place where all the foreign traffic that comes from the internet, and who knows who sent it, comes into OKD, correct? And if that traffic was able to tickle some bug inside of OKD, then the attacker would have super user privileges on the machine that runs all these other services. And once the attacker has super user privileges, he or she has complete freedom. You can do anything, right? There's no permission checks anymore that actually would stop you from doing anything, because you are the super user. You're basically the administrator of the machine. So the way they do this, correct, is that they have another process called OKLD that actually does the setup. So it brings all the services, including OKD, into existence. And it runs once, almost in the beginning, and it runs actually with super user privileges. And so in fact, what it does, it actually opens, for example, the port 80 connection, and then hands off the port 80 connection to OKD, and running OKD with not that many privileges, like a normal, ordinary process. All right? So that's the role of OKD, and basically it sets it up, and it does it once, like in the beginning. This is why the arrows in the paper are dotted here, because it's actually a one-time setup. Okay, yeah.
How does that minimize the severity of an attack?
Well, hold that question for a second. I'm going to go through each of these modules in a second and talk about what's the attack surface and what's the harm if that service would be compromised. This is exactly the right question to ask. Okay, let's make sure that we complete the picture. What other services are there in OKWS? Yeah. Yeah, there's the logger is here. Also launched by OKLD, and people, the different services can do RPCs, to the logger. And why have the logger as a separate, isolated component? And why is it important for security? Yeah. Yeah, this is for after recovery, right? Like, let's say your site does get compromised. It'd be nice, to find out later, what actually really happened. And so you want to make absolutely sure that, what the typical attacker would do is, the first thing we would try to do is, erase, their traces, correct? And probably try to remove the logs. And so the logger runs into a separate isolated domain to make sure, or to at least increase the chances that the attacker won't be able to delete any log records. Yep. Okay. Okay, so these are the main servers. There's one more. It's not so important for our discussion. pubd, which has the templates for the static web pages and to serve actual web content. Okay. Any questions about this picture? It's not as nice looking as in the paper, but hopefully still readable. Okay. So now we want to, we talked a little bit already about the motivation for why the service is in this way. But we want to do a little bit more detailed discussion. Sort of really look into why why does this buy us some extra security. Right? So in a way we want to go about this is to basically maybe make a table by service, and we're going to look at what how bad is it, or what problems would it cause if that service would be compromised, and we're going to label that the harm that can be done by the attacker by compromising a particular service. And then we want to understand the service that the attacker is available to basically exploit bugs in the service. And ideally, of course, for every service, the answer is absolutely no harm if it's compromised, and there's no attack surface, which of course is never true, but that would be the ideal outcome. Okay, so let's go one by one and discuss them. So let's start with OKLD. So what's the harm if OKLD is compromised by the attacker? Yeah. Yeah, it runs as root, right? So everything. So big harm. Let me just write that down as so it'd be terrible. So what's the attack surface that OKLD has?
Maybe loading the service if you can somehow modify it, crash it. But that's like very hard.
Yeah, the attack surface like just to first order, the attack is incredibly narrow and almost inaccessible, correct? And actually, the surface, if you look at this picture, it's not connected to the internet in any particular way, correct? There's no service that actually is allowed to make RPCs to OKLD. And so in fact, there's like no direct interaction between what the attacker can actually, there's no interface that the attacker can even sort of invoke, right? And the fact that it also doesn't take any user input. It just starts once, and I think the only thing you can do to it is send a control signal to it to restart. So the attack surface is incredibly narrow. And you see why this is now the case, correct? Because if the attack surface was not very narrow, then presumably the attacker had more opportunities, and then we might actually be in serious, serious trouble. So it's carefully designed to actually have a very narrow surface, attack surface. Okay, let's look at the next one. OKD. Well, let's say OKD, correct, is the thing that actually talks to the internet. It's written in C or C++ in this particular case, sort of similar to like the daemon you've been looking at in Lab 1. And so what could happen if an attacker exploited a buffer overrun in OKD? How bad would it be? Yeah. Could bring down the website for sure. So let's just take this whole discussion of sort of denial of service as a separate problem. And just mostly think about confidentiality and yeah.
Could they spoof their own requests on all the services?
Yeah, presumably, okay, so they're going to be sitting here basically interposing on they have complete control over all HTTP traffic, right? What comes in and what comes out. So the attacker, if compromises the OKD, it can interpose in every HTTP request. And basically call, what can it do? It can actually invoke RPCs to all the other services, right? And cook up, privileges, send them to the service, do RPCs, whatever, do a dating or a matching thing, or issue a profile, or issue an RPC to the messaging service, and basically it can send a lot of RPCs, right? Can it get to the database? No, not directly, right? In fact, OKD doesn't talk to the database, even to a database proxy directly, right? The only way to get actually to the database proxies is through the services. And so OKD itself doesn't directly talk to the service. So most likely, to first order, correct, it's not the case that if an attacker compromises OKD, then it can actually take all the user data out of the database. That's probably unlikely to work directly, right? What the attacker has to do is basically compromise one of the other services to actually be able to do that. Does that make sense? So what is the attack surface here in OKD? It's narrow, big, tricky, easy to exploit.
Really big.
Yeah, basically any HTTP request, right, is part of the sort of attack surface. And so anything that the attacker could do to manipulate HTTP traffic or cook up bad HTTP traffic is all part of the attack surface. And so it's a sizable attack surface. And particularly, but just to be a little bit precise, how much of the HTTP traffic does actually OKD look at? So if a request comes in, does it look at everything to base its decision on, or?
It only looks at the first part of the path to figure out where to route it.
Yeah, it only looks at the first line, right? Namely, enough just to make a decision about which service actually should deal with this particular request and turn it into an RPC. Right? Yeah.
Look at like the cookies and stuff though.
Sorry, Dan?
Wouldn't it also need to look at the cookies to know like which user?
Yeah, so presumably, at some point during logging, there's some set of a cookie, and it will forward that cookie along with the RPC. Yeah. Does that make sense? So why is it a good thing that it only looks at the first line? And what could go wrong if it looked at, if you look at one line, let's look at 2 lines, how bad can that be? Like what is hard in processing an HTTP request, or an area where people typically make bugs? Think about lab 1. Yeah.
If it's a very big request, you can maybe have a buffer overrun, but if the first line, you can do it in a streaming way. So
so you think about it, like I think in general what the hard part is like parsing. Yeah? So you get a bunch of bytes in from the network, and you have to parse it into an HTTP request and understand what it is. And it just turns out to be very tricky to get right. It's easy, because it's pointer manipulations, it's looking at the, and so it's easy to get buffer overruns. And so one line, looking at one line probably allows them to limit more precisely, how big the buffers have to be, et cetera, right? So this is why, it's designed in this way. Okay, let's look at a couple more. OK log D. So let's say an attacker is able to compromise OK log D. How bad that be? What's the impact of that? What's the harm of compromising OK log D? Yeah, go ahead.
They can trash the logs. That's about it.
Yeah, trash the log. Can they trash the database? No, correct? Because the logger actually doesn't have direct access to the database at all. In fact, it doesn't talk to a DB proxy even, correct? And so presumably what's going on here, correct, is that the logger has its own storage, private to itself, and that is not shared with any other service. So the log can be erased, but hopefully nothing else bad can happen. What's the attack surface here? What does the attacker have available to try to launch an exploit? It's pretty narrow. What is it? Just a big, what is it? The RPCs, correct? So whatever RPCs the logger supports. And presumably those are going to be very simple, right? Log record. Maybe there's only one RPC, and that's it. And so maybe there's not much opportunity for even an attacker to exploit a bug in the logger if there were one, because it's very actually hard to trigger it in the first place. Does this make sense? Okay, so let's look at the services. And this is sort of generic. So any service. What's the harm? Same free? Yeah, go ahead. Well, one of you. Go ahead.
You can try to get something. You could probably get something from the database.
Maybe. Let's ignore the database for a second and talk about that for a second. What is in the memory of this service? Yeah, some user data, right? Data that was loaded by the servers from the database earlier. The attacker compromised it. There's all kinds of stuff in memory, correct? And in fact, in this particular case, you remember that the separation plan is by service. And so one service might be operating on behalf of multiple users. Right? For example, the matching service most likely has user data from multiple users in its memory. Right? And so if you compromise that, then you'll have access to that data. So what's the harm is whatever the data used by the service. And it's likely to be user data. Right? And so this, in some sense, it's a bad outcome. Right? This is like a thing that Max wants to avoid. He wants to leak as least amount of user data as possible. And so it seems like too bad, correct? Like when you compromise a service, then naturally you get access to user data. Do you get access to all user data? No. Correct? Go ahead, yeah.
Only the subset of the data which is associated with that service. The idea.
Yeah, whatever data that service has access to, you might be able to get access to, but no other data, correct? So maybe for the matching service or whatever data that's necessary for matching, you might be able to get access. But do you get access to the password table? Probably not. The user table, probably not. The profiles, the photos, maybe not. Maybe, right? It's unlikely. So basically, it's bad, but it's only partially bad. Right? Yeah.
Aren't they defining the granularity of the services and what sort of?
Yeah. So absolutely. So hold on to thought this for a second. So if this was like, okay, it is definitely the developers. I think the way to think about it is that there's a team of people, security-oriented people that really make the decision about like what should be in each box, and so like how to split up the services. Once you decided, you're going to implement some service I, then you get the inexperienced programmers and say like implement service I. Right? And so the decision about how to split it up in the different services has to be done with somebody that actually security-minded. Right? And it's going to be forced. It's going to be enforced in some sense by the database proxy, right? Because the database proxy provides the RPCs that the different services need to actually get to their data. And presumably, just take it a little bit literally, Max is in control of the database proxy. He decides, what RPCs you're going to get. And as a service developer, you will have to come to Max and say, like, I would like to read this data, so can I access this RPC? And Max is going to say yes or no. Right? Or say, like, you should design your service differently so that it actually has to have access to less data. And here you see, correct, why privilege separation is not straightforward. It is very application dependent. And it's not like, okay, well, I want to do privilege separation, I'll follow the recipe and I'm done. No, you will have to start thinking about it, actually, how you're going to do it. Yeah?
So this paper seems to be implying that like compromising a given service is independent from compromising a separate service. Like it would be dramatically different. But in practice, if somebody can compromise any given service on this web server, wouldn't they likely be able to compromise anyone that they want?
Great question. And really, this is like question number 2, how to isolate. Like, if the isolation is bad, this whole plan doesn't work, right? And so the isolation has to be very good. Let's hold this question for a second until we talk about isolation mechanisms. But it's a key concern. Okay. So how we basically said, okay, well, servers can only access the data that it is allowed to access, right? And is this really true? Because like once its service is compromised, can it invoke any RPC of the database proxy? At least we haven't discussed any mechanism that would prohibit that, correct? Like once the service is compromised, that process, the attacker presumably has control and can basically issue any RPC, right? And presumably then get the data from the database of whatever the RPC returns. Yeah, or yeah, good.
Well, so are you like leading us to the token aspect?
Yes. Very good. Maybe you should come here and give a lecture.
So each service has their own token, and based on that token, you have limited RPCs.
Yeah, correct. I wrote it down a little bit earlier. Every service has a unique token, and there's access control based on the token, right? So if one service is compromised, like service N is compromised, the attacker will have service N's token and can issue the queries to the proxy for service N, but can it actually issue queries for another service? No, because it doesn't have the token, right? So where did the tokens come from? How did the service acquire their token? Presumably this is an important part of the security, correct? Because if any service just can get a token or cook up the right token, then we'd be in bad shape. So where are they coming from? Yeah. Yeah, OKLD, correct? OKLD launches these services, and when it launches it, it's actually going to give the token to that service. But then OKLD disappears, and it's gone from the picture, basically. Yeah?
When we already have unique users for each service and also the process ID, why can't we use that?
Yeah, there are many ways, other ways you can do it. And in fact, we'll see in lab 2, you can do it in slightly different ways. They chose to do it this way.
You can leak your token, but you can't leak being a certain process on the OS.
You cannot. We'll talk a little bit more about it. Again, this comes down to like exactly what the isolation mechanisms are. Yeah.
This would give you more attack surface in that you can sort of join exploits and two services together. So suppose one service you can't arbitrarily execute code, but you can get the token. Another service you can't get the token.
Yeah. If the attacker gets compromised more and more services, it's going to get more data, right? And if it can attack compromise all services, certainly it will have access to almost all the data that's in the database, right? So it's not a bulletproof scheme, right? It just makes life a lot harder, for the attacker, right? But really, what our goal here is to make sure that if one thing gets compromised, not the whole website is compromised. Okay, so before we dive into the isolation mechanisms, let's discuss a couple design decisions. We sort of understand why it's designed the way it is and what the role of the different pieces are. So why the separation by service? That seems like the fundamental choice they made, correct? Why? So what other plans could you imagine? Yeah.
By user.
Yeah.
If you do some sort of matching operation, you'd have to lock all the users.
Yeah, so the one obvious plan, I think most systems will use that as the default plan, is to do it by user. As I mentioned earlier, like for example, you implement an email service. The user only has to look at their own data, and so there's no reason to do anything complicated. You can just do it by user. And they clearly decided not to do that, right? And I think the reason is, as you exactly pointed out, is like for some services do have to look at the data of other users. And so this is the reason why it's done in this style. What other things could you think of? What other rules could you use, sort of like high-level separation rules? A little bit more, okay, a couple others that you might think about. You could do it by, like, say, bugginess. Like, many particular components of the systems maybe likely to have more bugs than other components of the systems, and you put those in separate boxes. Like, in some ways, this is exactly also what OKDOS does. It puts all the sort of more likely buggy applications, the services written by inexperienced programs, in their own box. Right? Another rule that you could imagine is like, well, we separate by privilege. So something that has to have high privilege, we'll stick it in a separate box. And maybe nothing else. And in some ways, OKDOS does that too, right? Because it puts OKLD, which actually is the most privileged piece of this whole picture, into a separate box that only runs at startup time. Right? Another thing you could think about is maybe you'll separate by exposure, or like attack surface. So for example, and in some ways, this website does it too, because OKD presumably has the biggest exposure, and so that is like limited in what it actually does, and it's like a small little box that only looks at the first line of the stuff that comes from the internet. Right? So these are also different ways you could think about splitting your software up, to get better security. Okay, so this is separation by service. Hopefully that is clear now. Oh yeah, where should the in this design, where should the attacker focus? I mean, the system could still be attacked, correct? And if you were an attacker, where would you spend your energy? Yeah, go ahead. On the service, for sure, right? Because that is, if you're successfully compromised the service, you at least get some of the data that's actually in the website. So that seems a good plan. Any others? Yeah. Yeah, I mean, tokens would be good if you could get them. Might be hard because you have to compromise multiple servers to basically get handle of the tokens. Yeah. OKDs is definitely good to buffer overruns. There's presumably going to be some. They're pretty careful, correct? Like, what do they do with libraries? Does actually OKD run with all the system libraries that the system has available? You think about lab 1, correct? If you compromise, do a buffer overrun in the service, what were you able to do? You have full control, basically, of the machine. You could delete files, correct? You could do all kinds of stuff in the file system, right? So it seems like if you compromise OKD, this could be pretty bad, right? Because you might be able to, if we don't do anything in addition, we might be able to compromise, the hacker might get control of the file system. So what's the story for that in OKWS? Any?
Access other elements of the file system after you start running OKD?
Yeah, there's actually, the isolation plan is pretty strict. Every service, gets limited access to the file system. And in fact, OKLD gets very, very little access to the file system, mostly only to reach its own binary so that it actually can run, but that's it. Right? And we'll talk about it in a second. We'll come to this isolation mechanism, but that's clearly, any isolation plan, this must be part of the isolation plan. So otherwise you could pull off all the attacks that you were doing in lab 1. What else should the... So who enforces the isolation?
The operating system?
Yeah, the operating system. So what would be a good place to attack? The operating system, right? Because we get control of the operating system, we'd be in business, right? Are there operating system bugs that can lead to exploits? Meltdown, yeah. Well, though it's maybe hard to, at least a potential exploit. But is Linux bug-free? Like Plan A? Are there no bugs in Linux? No. Not, correct? In fact, every year there are a couple of buffer overruns in the Linux kernel too, right? And they do a great job. They try to make it as secure as possible, but there are problems once in a while. So presumably what an attacker could try to do is like take one of those 0-day exploits and compromise the operating system. You compromise the operating system, there's no isolation anymore, and basically things are in great shape from the attacker's perspective. Okay. Any questions about this so far? Or people get a sort of feel, what privilege separation means and why it actually is not that straightforward. And you will be struggling with a lot of the same issues in lab 1. We're going to basically give you a whole bundle of code that's going to look like one big program, and it's your job to figure out actually how to split it and insert RPCs and the appropriate tokens for wherever a token is necessary, et cetera, et cetera. Okay, so hopefully this is helpful if you're doing lab 2. Okay, let's talk about isolation, since there was a whole bunch of questions about isolation. So isolation mechanisms. And let me start sort of from a very high level and then drill in. So what, I mentioned earlier, the Google paper, the Google white paper, the Google architecture paper, talked about privilege separation too, right? And what isolation mechanisms did that paper use to isolate the different boxes of the system? Yeah.
One virtual machine.
Yeah, one is virtual machines, but what else? Did they dedicate physical machines to particular services? They do, right? So the easy way to separate, like one way to draw this picture, correct? Is to say, I'm going to dedicate a physical machine to each of these services. That's going to give me strong isolation, right? Because they're not going to share a file system, they're not going to share a disk, they don't even have the same operating system or the same kernel running on them. They're all completely independent, and the only way they connect with each other is through a network. So this is a popular way of actually doing isolation, physical machines. And it's probably one of the strongest ways of getting isolation. Right? Because we don't have to worry about any, like the question that you just asked, what happens if the file permissions are not set up correctly? It's not going to matter because it runs on a completely different machine. Make sense? So clearly physical machines is expensive. And so the next option is, as you suggested, is virtual machines. Almost as good as physical machines maybe, right? Because you're running n virtual machines on one physical machine, and each virtual machine has its own operating system, its own file system, and it's pretty isolated. If the virtual machine monitor does a good job, which it's supposed to do, right? It is completely isolating each virtual machine. Right? I mean, if you think think about lab, the lab infrastructure, correct? You're all running a virtual machine with the 858 code inside of that virtual machine. And I'm sure many of you in the beginning were like, oh, this is annoying, right? Because I can't get my files, from my file system. I can't use my editor. I can't use my, my favorite, development environment, correct? Because I have to SSH into this damn machine that these 858 staff people set up for me, and it's inconvenient, right? But that's the power of virtual machines in terms of security, is they provide isolation, right? You can just SSH into them and do your work. but you can't directly access from the virtual machine any other files that may be sitting in the host or any other virtual machines. Right? So another way of implementing this picture, right, is to sort of run n virtual machines, one virtual machine per service, right, on one single physical machine. Okay, what's the downside of doing that? It seems totally possible, correct? What is the downside? Yeah. Yeah, it's quite a bit of performance overhead. It's actually, a virtual machine monitor does add, to the cost in terms of performance. You have leaving and entering the virtual machine monitor, and so that actually turns out to be reasonably expensive, and for some websites, too expensive. So the third option, which is what the paper basically exploits, is to say, well, the operating system provides isolation as it is. I mean, a Unix process is in some sense isolated, right? Well, like one Unix process cannot scribble over the memory of another Unix process. So, and that's enforced by the operating system. The operating system provides, separation, right? And so, why not use Unix processes? And that is another popular way of doing it. That's exactly what the paper did, right? The paper uses, Unix processes plus a whole bunch of other mechanisms to actually do that. So I'll talk a little bit more about that in a second, what the paper actually does. Today, I think most people say, well, it's actually really hard to get that strong isolation using Unix processes. You have to use the Unix system calls very, very carefully. And if you do that really right, you can get it. But it is cumbersome, and it's not that straightforward. And so there's almost like decades of research in operating systems to actually figure out like a good isolation mechanism. And the current popular one is containers. And that's actually what we'll be using in lab 2. And one way to think about containers is they're basically Unix processes, but really locked down. And so that you as a programmer don't really have to worry, if you have to set up like a process isolation, you don't really have to worry about it. The container system or the container package does it for you. It basically locks down the process in a way that it's very hard to escape that process. I'll talk a little bit more tomorrow about it in detail, how that happens, and I'll talk a little bit about it now and see how it works. Okay. Okay, so let's see in what way, or like a little bit get a feel for why it would be tricky to do isolation using Unix processes, so like the way the paper does. So an example of processes. And let's focus on only one process, because it's actually almost the most interesting case. Remember, OKLD starts with a lot of privileges. It's super user, correct? And it actually sets up all the other services. And so it's interesting to think about, like, what mechanism does it use to actually set up these other services, right? So let's focus on maybe starting OKD, how that happens. So what does OKLD do? Well, OKLD creates a new process, right? That's process. What else does it do? Or what does OKWS exploit? So OKLD runs with, what is actually the user ID for root or super user? Does anybody know? So every process in Unix has a user ID associated with it. And the user ID for root is the most privileged user ID. And everywhere in the kernel, when a process does ask for a resource, and the kernel sees that actually this is a user ID, the root user ID, the kernel will say, yep, you can have it. Correct? And so what do we need to arrange? What do we need to make happen? Well, we need to make happen that basically OKD runs with a different user ID than actually OKLD, right? And so there's actually, it turns out that Unix has some system calls to make user IDs or allocate a user ID. And so a process that runs can actually allocate a user ID. And these are sometimes called anonymous user IDs because they don't correspond to an actual user that is logged into the system. And it just corresponds to a unit of isolation, if you will, or a principle. And so with that, basically the OKLD can creates a new process, allocates a new user ID, and then the process drops its privileges to the user ID that is given. Right? There's a system call in Unix called setUID that allows a process to drop its privileges to something limited, particularly to another user ID. Right? And that's what actually OKLD does. It forks off a process, allocates user ID, and drops the privileges in that process to the one of the allocated user ID. Okay, that doesn't deal with the file system yet, right? Because now the file system is still shared among all processes. And so in Unix, there's another system call called change root, mentioned in the paper, that takes a directory as argument and basically changes the root, the top level of the file system for that process to whatever the directory is. So if you do cd/ inside of that process, it will go to the directory and not to the original top level directory. So what does this mean? So a process that executes change root to a particular directory, it can only access files within that directory tree and not any files outside of the directory tree. They're not even visible to that particular process. Does that make sense? So what should happen? Let's say you have a process, you change rooted it to like this new directory, and then inside of the process, maybe it's compromised by the attacker, the process does cd ... What would happen if the operating system were not implemented correctly or had a bug? Now you'll be able to escape out of the directory tree, correct? So certainly cd ... should not, should absolutely be carefully written so that it doesn't actually go outside of the directory. And there's a whole bunch of other exceptions like links and symbolic links that all need to be careful, sort of guarded so that they force the process to stay within the file system or the namespace of the file system that actually has been allocated to it or it has been restricted to. Okay, so you can get a sense, already that sort of setting up, that work, what the work that OKLD does is a little bit tricky. You got to be very careful. Use the Unix system calls in a careful manner. And so that's why, containers have become popular because they provide sort of a default strong isolation plan that doesn't require a lot of setup because the containers setup does it for you. So let me talk a little bit about containers. So basically containers are processes. So they're still as lightweight as a process, but with strong isolation. And just to make that point a little bit clearer, so for example, a container by default runs with its own file system. So you don't have to worry about change root, or at least the container implementer does it for you, but as the container user, you're basically thinking about a Unix process that actually has its own file system. In fact, how many of you started on Lab 2 and did the first piece of Lab 2? Nobody. That's a fun lab. You had a long weekend. Sorry. So if you look at a lab in a little bit more detail, you will see that basically the way you start a container, you basically start a container from a virtual machine image. And so the container runs, if you will, with the file system of the virtual machine image and has no access to any other file system. It only has access to its own file system. Also, containers basically have their own IP address. So they're completely they're basically like little virtual nodes or machines or processes that behave like virtual machines. They have their own file system, they have their own network address. You basically, the only way to actually interact with them is really set up a TCP connection with them if they're listening on the other side of it. And so they provide basically sort of the isolation of a virtual machine monitor, but using Unix processes mechanisms. Does that make sense? And tomorrow we'll talk a little bit more in detail about it. So here's another example to give you to illustrate what the difference is between sort of a regular Unix process and sort of a container Unix process. A Unix process, can it actually poke at other processes on the machine? Or see the other processes that are on the machine? What do we think? Well, if you're in the shell and you type PS, do you see other processes? Yes. So it has to be the case, correct? That, there's a way of being interacting with other processes on the machine. And so there's a bunch of system calls that allow you to send signals to other processes. The way to observe them, maybe you want to debug them, and you can attach a debugger to them. And so there's all kinds of other sort of system calls you may not think about that actually most Unix systems have that you could use if you were an attacker to basically get control or influence another process. Right? And containers just don't allow you to do that. In a container, you cannot see the other Unix processes that are actually on the system. It is not visible to you. And one way to think about this is that the operating system, the kernel, has a lot of namespaces, like the file system namespace, the process ID namespace, and a bunch of other namespaces. And what containers do, they basically isolate those namespaces. Every container gets its own process ID namespace. Every container gets its own file system namespace. Right? And that ensures strong isolation because now the container, the thing that runs inside of a container, can't even name or can even observe or can even see the other things that are actually running on the system. Does that make sense? That's the high-level plan of the container sort of solution. Any questions about this? Okay, good. So tomorrow we're going to talk a lot more about containers and how you create them, how you make them, how you get files into them, because that's all the mechanism that you're going to be needing to actually do lab 2. You're going to be setting up containers, left and right, for these different services. You got to arrange communication between the different services so that you actually can implement, you can access to the database, et cetera, right? So to summarize, basically the lecture for today, we talked about basically the main topic for today was privilege separation. Right? And you can see, I started out like the design, the goal is to design systems in a way that they can tolerate bugs. And it's an incredibly powerful idea. And it's a widely used idea, but it's actually not that easy to apply in practice, because it's typically application specific or system specific. And so OKDOS was a way of a case study to sort of see what kind of thinking goes into doing privilege separation. And basically, it all comes down to sort of this table here, right? Where you want to split the system in different pieces, and you want to set it up that basically compromising any of the individual pieces doesn't do much harm, and in a way so that in a way that the attacker has very limited attack surface to actually get to these different pieces. Okay? All right, see you tomorrow.